Right, following on from the previous video, we're now going to show that any function f of x where the first n derivatives at x is equal to 0 exists can be written as a polynomial of order n, and as I remind you, this is known as Maclaurin's series. So, suppose we write that a particular function, provided it is differentiable and we can find the value at x is equal to 0, as a plus bx plus cx squared plus dx cubed plus ex to the 4th plus fx to the 5, etc. And we've got to be able to find the values of a, b, c, d, e, f, etc. Okay, if we put x is equal to 0, that's great. Okay, this side we have f as 0, and this side, all these terms here will disappear because 0 times anything is 0. So we'll just end up with f of 0 is equal to a. We'll highlight that. Okay, now if we differentiate again, we're going to get f dashed of x. The a will disappear. We'll just get b from here. We'll get 2cx from here, 3dx squared plus 4ex cubed plus 5fx to the 4. Now, if we put x equal to 0, on this side we'll get f dashed of 0, on this side we'll just get b because all these terms will disappear, and then anyone's after as well, which means that b is equal to f dashed of 0. Right, if we now do the second derivative, the b will disappear and this will now become 2c plus 2 times 3 times d, I'm going to write it like that on purpose, times x, plus 3 times 4 times ex squared, plus 4 times 5 times fx cubed. And again, if I put x is equal to 0, all these terms will disappear. We're just going to get f double dash of 0 will be 2c, which means that c will be f double dash of 0 over 2. But instead of writing 2, I'm going to write it as 2 factorial, and you'll see this when we sort of get the next few terms. All right, so writing that out again up here. Okay, so what we're going to do now is we're going to differentiate again. So if we differentiate again, the 2c will disappear. And we'll end up with 2 times 3 times d plus 2 times 3 times 4 times ex plus 3 times 4 times 5 fx squared. And if we now put x is equal to 0, these terms will disappear and any after, and we'll get the third derivative of 0 is equal to 2 times 3 times d, and we can say that d is the third derivative at 0 divided by 3 factorial, because 2 times 3, we haven't written the 1 in, but 2 times 3 is 3 factorial. Okay, differentiating again, this term will disappear because it's a constant term. We're just going to get 2 times 3 times 4 times e, and then 2 times 3 times 4 times 5 fx, and then it will carry on all the other terms. Putting x is equal to 0, we're going to get the fourth derivative of 0 is equal to 2 times 3 times 4 times e, and therefore e is going to be the fourth derivative at 0 divided by 4 factorial. Now differentiating again, we're going to get 2 times 3 times 4 times 5 times f. So f will become the fifth derivative of 0 divided by 5 factorial. And then we can keep repeating the process. The sixth derivative would be the sixth derivative at 0 divided by 6 factorial, for example. So the process continues. Okay, so writing those all out, so my a is f of 0, b is f dash of 0, c is f double dash of 0 over 2 factorial, etc. Okay, my expansion that I started with will be a plus bx plus cx squared plus dx cubed plus ex to the 4th plus fx to the 5. If I now replace a, b, c, d, e, f with these, I now get f of 0 plus f dash of 0x plus f second derivative at 0 divided by 2 factorial x squared plus the third derivative at 0 divided by 3 factorial x cubed plus the fourth derivative 0 divided by 4 factorial x fourth, plus the fifth derivative at 0 x to the 5, then there will be some last term which would be the nth term, the nth derivative at 0 divided by n factorial over x to the n. And here we have the general term, f of x, 0 x to the r over r factorial. Okay, and this is known as Maclaurin's series, okay. Okay, so this has been a video to establish Maclaurin's series. I hope you've understood, and I thank you very much for watching.